Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into DDoS protection, the architecture that keeps web applications online during massive distributed denial-of-service attacks. We'll cover how Cloudflare, AWS Shield, Akamai, and other platforms detect volumetric, protocol, and application layer floods, scrub malicious traffic at the edge, and challenge suspicious clients without blocking real users. Whether you're preparing for a senior engineering interview or defending production infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into DDoS protection, the set of strategies, services, and architectural patterns that keep web applications online when they face massive, distributed denial-of-service attacks. If you have ever wondered how platforms like Cloudflare, AWS Shield, or Akamai Prolexic absorb hundreds of gigabits per second of malicious traffic without dropping legitimate users, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building resilient infrastructure, let's get into it. Here is the core problem. A popular e-commerce site, payment gateway, or API service is running normally. Suddenly, traffic spikes by 1,000 times the baseline. Requests come from thousands of IP addresses, countries, and devices. Some are simple UDP floods. Others are HTTP Layer 7 floods designed to exhaust application resources, and still others are slow lorries or connection exhaustion attacks. The origin servers saturate, databases lock up, load balancers fail, legitimate users see timeouts, and revenue stops flowing. The business needs a DDoS protection system that can detect attacks in seconds, scrub malicious traffic close to the source, challenge suspicious clients, and only send clean traffic to the origin. The protection must work at network layer 3, transport layer 4, and application layer 7, and it must scale automatically. Let's walk through the functional requirements. First, the system must monitor traffic continuously across all network layers, collecting metrics like packets per second, bits per second, connection count, request rate, and request signatures. Second, it must detect anomalies using both threshold-based rules and behavioral baselines, distinguishing flash crowds and viral traffic from malicious floods. Third, it must mitigate attacks through multiple techniques: rate limiting, IP reputation filtering, geo-blocking, challenge pages such as CAPTCHA or JavaScript challenges, automatic traffic scrubbing, and black hole routing when necessary. Fourth, it must provide real-time visibility through dashboards, alerts, and post-attack reports that show attack volume, vectors, sources, and mitigation actions. Fifth, it must integrate with DNS, CDN, Anycast, load balancers, and cloud provider networks so that protected traffic is routed through the protection layer before reaching the origin. These 5 capabilities make the protection active, not just reactive. Now the non-functional requirements. The system must be extremely low latency because adding DDoS protection should not degrade the user experience for legitimate traffic. Detection must be near real-time, ideally within seconds, because a 30-second delay can already overwhelm an origin. The mitigation must be accurate. False positives block real customers and lose revenue, while false negatives let the attack through. The system must scale horizontally to absorb the largest attacks, which can exceed hundreds of gigabits per second or millions of requests per second. High availability is critical because the protection layer itself becomes a single point of failure if it goes down. The system must be cost-efficient, since attackers can scale cheaply and defenders must not spend unlimited money on every attack. Security and privacy matter because the system inspects traffic, terminates TLS, and may challenge users. And finally, configurability matters. Different customers need different thresholds, whitelist rules, and compliance requirements. Here is the high-level system architecture. On the far left, the internet contains both legitimate users and botnets. Traffic first reaches the Anycast network edge, which announces the same IP address from many globally distributed scrubbing centers. Each scrubbing center runs a network layer 3 and layer 4 mitigation layer that filters UDP floods, SYN floods, and connection exhaustion. Clean traffic or traffic that survives the first layer moves to the application layer 7 proxy and web application firewall. This layer performs TLS termination, bot detection, rate limiting, challenge pages, and request fingerprinting. A control plane continuously collects flow data, metrics, and logs from every edge location, runs detection algorithms, and pushes mitigation rules back to the edge. A management console and API let operators and customers configure policies, view dashboards, and receive alerts. A SIEM or analytics backend stores forensic data for post-attack analysis. The origin only sees filtered traffic, preserving its availability and performance. The key metrics to memorize cold. Attack bandwidth, measured in bits per second or packets per second, tells you the raw scale. Legitimate traffic rate, measured in successful requests per second, tells you whether the service is still usable. Mitigation time, the seconds from detection to scrubbing activation. False positive rate, the percentage of legitimate users blocked or challenged incorrectly. Challenge solve rate, the fraction of suspicious clients that pass a JavaScript or CAPTCHA challenge. Origin offload percentage, how much of the total traffic the scrubbing layer absorbs so the origin does not have to. Scrubbing capacity utilization, the percentage of available scrubbing capacity currently in use. And mean time to mitigate, the average duration from the start of an attack to full mitigation. These metrics are what the operations team and the business actually care about. Let's trace the end-to-end user journey. A security engineer at an online retailer configures DDoS protection for the storefront. She points the DNS record to the Anycast IP address provided by the protection service. Baseline traffic patterns are learned over the next few hours. During a flash sale, the platform sees a sudden surge. The detection engine recognizes that the request rate is 10 times baseline. Many requests share the same user agent, and the geographic distribution is abnormal. Within seconds, the system automatically enables rate limiting, presents a JavaScript challenge to suspicious sessions, and scrubs traffic at the edge. The engineer receives a dashboard alert showing attack volume, top source countries, and blocked IPs. She confirms that legitimate checkout traffic continues to flow. After the attack subsides, the system generates a post-attack report with full forensic details and recommendations for tuning thresholds. The core models and algorithms. Traffic baselining uses historical data to learn normal patterns by time of day, geography, endpoint, and user agent. Anomaly detection applies statistical thresholds, machine learning classifiers, or entropy analysis to detect floods, reflection attacks, and application abuse. Mitigation policies are rule sets that map attack signatures to actions. Allow, challenge, rate limit, drop, or black hole. The IP reputation database stores known malicious IPs, autonomous system numbers, and botnet fingerprints, updated from threat intelligence feeds. The challenge framework decides when to present a JavaScript challenge, CAPTCHA, or proof-of-work task and tracks solve rates. The Anycast routing model distributes traffic across scrubbing centers and can withdraw routes from overwhelmed locations. Rate-limiting algorithms include token bucket, sliding window, and leaky bucket, applied per IP, per session, per user, or per API key. The key trade-off is between aggressive mitigation, which stops attacks quickly but may block legitimate users, and conservative mitigation, which preserves user experience but may let some attack traffic through. Now the low-level design deep dive. The edge proxy is implemented as a set of stateless reverse proxy workers behind a load balancer. Each worker maintains a local cache of rate limit counters and IP reputation entries, backed by a globally distributed key value store. The WAF engine evaluates rules in a priority order. Exact match rules first, then signature rules, then behavioral rules. A separate detection service ingests flow summaries, HTTP access logs, and connection metrics from every edge, computes baselines, and emits mitigation directives into a control queue. The scrubbing center runs a network layer packet filter based on eBPF, XDP, or specialized hardware that can drop attack packets before they reach the proxy. TLS termination happens at the edge with certificates and keys managed by a secure key store. The dashboard API reads from a time series database and a relational policy database. The alerting service evaluates customer-configured thresholds and routes notifications through email, Slack, webhooks, or SMS. All components are deployed in multiple regions with health checks and automatic failover. Key takeaways for your interview. First, DDoS protection is a layered defense. Network layer scrubbing, transport layer filtering, and application layer challenge and rate limiting all work together. Second, always start with Anycast and edge scrubbing because absorbing traffic close to the source is the most scalable approach. Third, detection is a trade-off between false positives and false negatives, so discuss baselines, thresholds, and challenge pages as a way to reduce collateral damage. Fourth, rate limiting is not enough on its own. Combine it with IP reputation, bot detection, geofencing, and application-aware rules. Fifth, remember the operational side. Dashboards, alerts, forensic logs, and post-attack reports are just as important as the mitigation engine. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for DDoS protection. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on DDoS protection. We covered the full picture from Anycast edge scrubbing and L3/L4 packet filtering, through WAF rules, rate limiting, challenge frameworks, detection baselines, and the low-level design of the edge proxy and control plane. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.